Let me go with session share. I guess I'll start. I think the session share is just looking for a laser pointer, but with the screen small enough, shouldn't be a problem. Hope everybody's properly caffeinated, though I don't think you'll need it. I think this is pretty exciting stuff. So yes, I wanted to give you, basically it's a short introduction into machine learning and doing it in Python in particular. It's an impossibly broad topic to handle right now, but what I wanted to show, especially this kind of conference, is that it's rapid enough development, just like you think of Python as a rapid development environment in terms of general coding. This is rapid development for machine learning. And even for small tasks, even if you're not tackling a big analysis task, prediction algorithm classification task, sometimes you just need to construct a quick model or learn a bunch of rules automatically and incorporate it into your software. This is really nifty. So first to introduce machine learning, because I don't expect this to be a prerequisite for this session. The idea is you teach a computer to recognize patterns, to do something a human would do otherwise. And broadly speaking, the field has three subcategories. You can do supervised learning, which is you give the computer the data, the input data, based on which it should construct the model. You give it the appropriate, whether tags, whether it's the correct result in a continuum, whatever it is, and you say, learn to combine the input variables to give you the target. Thank you. Oh, we'll do it here on the screen, but thank you. So, and broadly speaking, we classify these into classification tasks, where there are a few discrete categories that you are categorizing your sample data into. So think of it as the dependent variable just having a few integer values. And then there is regression, where you think of it as the dependent variable having continuous values, and you're just trying to find a model that can go through it. So this is the famous where you have scattered data points and somebody tries to find a best fit line through it. And then from that model, you can do prediction in the future, or you get a better understanding in the relationship between the different variables you have. This is something that physicians have been doing for a long time. Nothing new about this, but technically this is also teaching a computer something. So machine learning is really a superclass, the superset of all these techniques that statisticians have been done forever, and modern computing gives us a chance to do on a whole different level. Then there's a whole new aspect of it called unsupervised learning. This is a bit newer, where we don't know the answer. You expect the computer to find you patterns. Sometimes there are too many dimensions, too many variables to think about, that you could say, like, I know what the categories are and I know how to separate them. You have no idea about your data. You don't know how many categories there are. You don't know what you're looking for. You expect the computer to find some kind of intelligible patterns in it. That may be the final point in your analysis, or that may be just the starting point, and you'll iterate once you've defined what your categories are. Maybe you'll go for a supervised learning approach, or a more constraints on supervised learning approach. So there are many ways to go about it. But the point is the computer can find you a structure where you didn't know there was any before. This talk will mostly focus on supervised learning, which is the more common and more useful approach for most fields. And then there is a reinforcement learning, where there's a system to interact with. It's not like you have the correct answers for how to operate the system. You're not trying to teach based on that. So it's a bit in the sense that it's unsupervised, but there's a system that has a certain behavior, and the computer has to interact until it learns how to use the system. You define a metric based on, how efficiently you use a robot in a field, how quickly you can guide it through a certain set of obstacles, whatever it may be. The computer iteratively learns how to operate this thing. So, what are the applications? Prediction. You may you may want to predict specific categories for something based on previous classifications, or you might want to predict something quite a bit more fluid, like the price of stocks, like the weather conditions, how demand would vary looking into the future, resource use. Sometimes you want to allocate your resources properly and you don't know what to plan for, but you do need to make commitments ahead of time. Entity classification is the most common. You might want to classify customers in terms of what they need or what they will need. Spam filtering has been around for many years. In essence, that was a machine learned algorithm where from previous fraudulent emails, you learned what patterns are common to them. Fraudulent transactions is even more of an issue when you look at bank accounts and so forth. And then there's topic analysis, where you have text. You may or may not know what topics there are, but you want to understand, you want to find patterns based on certain keywords, phrases. There are many ways of doing it to split it up into various topics. Machine vision has been a big thing. You may know that this field grows out of a lot of work that's been done in artificial intelligence for decades. And it started with trying to mimic the human brain. It turns, and now there's a revival of this where you may have heard of neural networks, where they are being used again to do a lot of classification, a lot of work where you need really sophisticated nonlinear techniques, where a lot of simpler ways don't work anymore. So what a lot of these things do is they try to break it down. Instead of having a picture with millions of pixels, you try to find common patterns. So if you're looking for face recognition, what are the prototype faces, the eigenfaces, mathematically, out of which you can construct any other face? And with that, you significantly reduce the number of dimensions, as we said. And you can then take any face and say, it's 30% this kind of face, 20% this kind of face. And then you can save this kind of a model and apply it. And then you can look for face similarities, for example. There are sorts of techniques. And you often need this if you need to find somebody that you're looking for, whether it's a security application or what have you. You will not be able to have a computer say, this face equals to the face I've seen 3 years ago. Or even two identical pictures will have some pixels different. So you need to find that kind of a similarity. And this is where dimensionality reduction and understanding faces in terms of this kind of reduced set is very important. Natural language processing has been very big. Anything from understanding, speech translating, sentiment analysis, summarizing, all of that requires machine learning. And then the old-fashioned modeling, looking for a simple model with a few parameters that explains lots of data points. That's the smooth version of it. And then if you think about it, rule extraction, this is the discrete version of that. Instead of having some smooth math functions that describe a particular dependent variable, you might say what conditions need to be met. You might have a system where if the customer spent this much, but it's already February, and the weather has been like this, then this is what was the marketing condition. You can extract all this from more classification-based sort of modeling. And then there are recommendation systems. You've seen forever how Amazon tells you, you might be interested in this based on your previous purchases. How does it know this? Sometimes you've only done 3 things. It can compare you to many other customers, compare the items you bought to many other items, and there are very sophisticated filtering techniques that incorporate these sorts of things. So it's a very big field at this point. And in the pictures, I show you just some examples. Traditional modeling where you're doing standard fitting, you're trying to find the relevant dimensions where it's clear that where there's a pattern in particular dimensions. So this is no longer the relevant set of bases. It's now you want to think in a different set of dimensions. And often these kinds of rotations and rethinking about your problem is the most important step you can take. Just like the rethinking about faces is the most important aspect. If you go based on pixel analysis, you'll not get anywhere. And then this is what classification often looks like, where you have overlapping data and you're trying to find clusters, trying to find boundaries that will solve it. This is one of the more common things you'll be doing. So simple look at what classification really means with machine learning. You have these data points. Let's say I already gave you 2 parameters that you know about them. So let's say there are 2 categories. How would you categorize these? You have no idea. That's the whole point. The problem is it's not clear how to categorize. The computer has no idea what it's doing. You need this is supervised learning, so we'll give it another set where we have the answers. And we assume that the same patterns exist in the system too. So if you tell it that around here you have these kinds of points, around here you have these kinds of points, can you find a general rule so in the future we can separate real data and you'll be more or less correct? So one thing you can think of is fitting a line that has the most captured on this side of one category, the most on the other side, and try to minimize the impurities, because this is a mistake. In the future, if there are more things appearing here, you might think that it's these yellow points, but in fact it's these reds. So the trick is to find a model that does this most correctly. You might think that this is the answer. Does that make sense? According to this, it might, but do you really have enough data? How do you know that these are not statistical fluctuations that cause these to overlap? Most problems are difficult enough that they're not easily separable. There's some overlap, and there's going to be trade-offs. There are going to be false positives, but you need to make some kind of a trade-off. And to think that you can eliminate all of them by making an arbitrarily complex function to separate these is, well, not just wishful thinking, it's incorrect, because you're actually introducing more errors into this. When you have real data and you start making these squiggles, you might be actually, basically you fit not to the true patterns, you fit to the statistical anomalies, to the what happened by accident in your finite data set. And so you've just walked away from the real pattern.
What would this be applied to? Like a document and like you're trying to categorize a document, or?
Almost anything. What kind of customers do you have? Let's say you have 2 age groups. And often there are more categories. I'm just reducing it to 2 for simplicity. It could be what kind of document you have, what kind of media do you have. YouTube does this all the time, trying to categorize things. So there are many ways this goes. And what you do when you model is that you reduce these things to variables. You stop caring what it is, and you want to find the relevant variables and find a space where they can be separated like this.
So you could see, the example I've seen for this one is like you're selling 2 different cars, and this is age and this is income, right? Mm-hmm. So that would be a plausible scenario.
Yeah, that for this age and income, they tend to buy these cars, for this age and income, those cars. And of course, sometimes there are overlaps that somebody in their 90s wants a race car, so the applications are plethora. The question is, how do we make intelligible choices in this kind of a situation? So clearly, we're not happy with doing it like this, and this goes back to the statistical principles that you have only so many degrees of freedom. You have that means you have only so much information from your data. Every time you put in a new parameter in your model to fit, you're reducing the number of degrees of freedom. In general statistics, you know that your model has to have much fewer degrees of freedom than your data. So think about it like this. Every parameter you put in, you're subtracting 1 data point in terms of what you originally knew. And a less crisp way of thinking about it is that, and what often gets done in more sophisticated machine learning approaches is that you don't necessarily have to totally dumb down your model to something simple. If you do have some kind of a curvilinear aspects like quadratic, cubic things, you could just de-emphasize them. And that's what's called regularization, for those who are curious to look into this, and we'll be doing this for your work. So you don't necessarily have to cut off parameters, reduce everything, but you have to de-emphasize and understand that your first priority is to get the general pattern, and the rest is just polishing. So these are important things to keep in mind when you do this kind of work. And this is where a lot of the savvy in algorithm design and your use of the algorithms will come in. So general steps that you do when you approach these kinds of problems. First, you have to identify. I gave you these two variables from the start, but you might be dealing with a data set that has some input variables. You might have to collect and understand what the relevant variables are. But you might get variables that are very undescriptive. What we call they help you make weak predictors, and you might have to create new variables that might give you a better separation. And this is what this step is generally called feature engineering where you're trying to help your problem by creating better variables. And the other aspect of it is creating a better model. And these are two separate things. Sometimes people jump one on the other, not realizing which is the more important obstacle currently for their work. So this is where you think, is this plausible to have this kind of complicated model? Should I reduce it to something like that? Should I even be thinking in terms of these straight separators, or is there a more sophisticated approach? So this is what you think about in this latter step of classifier modeling. And it's up to you, the human, to come up with the general shapes that it's allowed to take. The what's the overall form, what kind of freedoms you want to give to the model. The tuning will be done by the computer according to the optimization of how many data points are captured to which side.
Would you call those parameters?
I'm sorry?
Are those model parameters?
Right.
Yeah.
Now, that said, there are non-parametric approaches, but even there, there are certain aspects that's fitting and certain aspects that you're tuning. Okay, so I want to give you a sample problem. It's been a bit abstract until now. I don't know if everybody has heard here of Kaggle competitions. If you want to get started in machine learning and data science, it's a great place to go. They have some very simple problems to get started on, and then there are some really advanced things that the scientific or corporate community really needs solved, and there are sometimes very large cash prizes for giving them a good solution. So I really recommend for anybody interested going to the site and checking this out. So the forest cover has been a famous problem. Thousands of people have tried to present their solutions, and it's a good way to cut your teeth in this field. So the basic question there is that, can we design a computer algorithm that will predict, given a terrain, given something you know about the soil, about the local geography, local the features on the map that the humans have put on, like roads and irrigation, can you predict what will be the dominant foliage, what will be the dominant cover for a forest there? And this because they've done surveys and they know the answer for certain tracts of land in the United States, but it would be a lot easier if we had if based on pre-existing surveys of other things, if the machine can just say the dominant tree over there is like this. So what we're given is for every patch of land, I forget the size, you're given, well, some administrative thing like an ID, elevation of where that tree stands, the slope of that terrain, and some more things relevant to this problem. We don't have to dive into the ecology at this point. And it has information like how far away from water, how far away from fire points, roadways, and so forth. So can you combine all these things to come up with a formula that will give you the correct classification? In this case, we're dealing with 7 different foliage types. So let me break for a minute. We have a problem. I gave you general ways about how you want to approach it, what kind of things you want to think about it, but what are actually your tools? How would you actually start coding this up? So I wanted to focus on Python today. Python itself is fairly powerful, has some math tools, but whenever you do anything with real math, you want to go to something more sophisticated. So you have the Numpy package, absolute must for any real computations. Most things you'll be able to do with Numpy. For more advanced things, like for instance, some statistical tests to make sure you really know what you're getting, like the Fisher test that I had to do in some of my work, you want to go to the Scipy package, which has more advanced and more domain-specific math functions. All of these that I'm describing are open source. Then specifically for what we're doing, machine learning, there's a really nice mature package called scikit-learn. It is based, it tries to keep itself compatible in terms of data structures with Numpy and Scipy. Most of what I'll be showing you today will be on scikit-learn. I really recommend it. Really gets you off the ground running really fast. So this is the background. This is what will actually be doing your work. These will be your workhorses. But to get yourself started, you want to get a feel for it. You want to make some graphs. You want to understand what your data is. Before the human's eye go on it, you have no idea how to make your model. You have to always iterate. Get some intuition, work on your features, work on your model, have it fit, understand what's wrong, why it's not accurate as you expected, and repeat. So you do want a good place for your eyeballs, for your own rapid diagnosis of the data. So one thing I would recommend, in addition to the basic data structures you would have in Python, like lists and tuples and so forth, it's good to have data frames. It's good to have series. It's good to have vectors, a way to do an operation on all your items simultaneously, just the way you do in math. You do a vector operation where you multiply two vectors. You don't care what happens on a dimension by dimension level. It's a high level thing, and you want to keep thinking high level. You don't want to get yourself bogged down. So Pandas is very good, very well developed, where essentially it's like when you have data, you have an Excel sheet in your memory, essentially, and you can do operations like I want these columns and I want this subset of indices, and it spits it out right away. You want a nice, comfortable environment, like if any of you have used MATLAB or Mathematica or Maple or something like that, you might find the basic Python shell a little bit lacking. So this is where IPython is very good. It has better history management. It has, depending on the packages, some markup of your code. It can show you your plots right there in your shell. So a lot of things that are very nice to use there. I highly recommend it. And then for plotting itself, the workhorse there is the matplotlib. All of these free, as I mentioned. So what does the initial exploratory analysis, I call it, how does it look like? So you were given this data set. You don't know what's inside. You definitely don't want to eyeball through the entire table of all the tagged data you were given on forest and look at all the soil types and elevation and so forth. You want to graph it and see how it separates. Elevation seems like an obvious thing. You know that some trees prefer to live at high elevation, some prefer lower. So what if we were just to plot for each category, for each of the 7 foliage types, what elevation? We want to make a histogram for each foliage type, for each tree, the histogram of their elevations. And this is what I've done for you. There are 7 colors. I made them translucent so you see the overlaps. And you see the code here is very simple. This is boilerplate code that you just set up initially. This will be at the head of all your work, whether interactively or in a script. And this is all it takes. Just a simple for loop with a histogramming did all of this. It can be even simpler. You can just say, iterate through the foliage types 1 through 7. But what I did is take all the cover types. This is the true labeled information. Take the set, basically get the unique list. So that gives you the 1 through 7 list. So the cover type is therefore the index, the identifier for that particular tree. And look how simple it is with these DFs, data frames from Pandas. The data frame is that Excel sheet, quote unquote, in your memory. You're saying that I want to query it, so you ask for a location where this is the indexing, where in terms of rows, give me those where cover type is of that type. So first one might be, I don't know, this black one. And I want only the column corresponding to elevation. So suddenly you have your list of data. For simplicity, to make it palatable to Matplotlib, you convert it to a simple Python list. And then these are the things to make it pretty the way I showed you there, to make it translucent so you can see what's going on. So this is the technical aspect of it. The machine learning aspect. What do you see? You see 2 tree types completely well separated. In theory, you don't need machine learning anymore. Human learner can already see that if I put a threshold here, I can tell between the blue and the black, whatever numbers they are. I guess 5 and 7 type for us. But you see that the problem doesn't ask you to just separate these 2 types. Clearly, these don't want to live anywhere near where these trees want to live. But there are so many other types, and they're all overlapping. So if you just went by elevation, it's still going to be messy. You're going to be making more mistakes than correct answers. You will already have something if elevation is all you knew. You definitely knew that at this elevation, you never have this kind of a tree. But this is clearly not enough. So what do you want to think about when you are selecting your features and when you are creating new ones? And how do you want to think about your data? You do definitely want to understand how clean your data is, whether they're missing values, and make sure that doesn't trip up your analysis. You want to think about correlations. This is something that's been bothering statisticians for a long time. And a lot of modern techniques regression or classification techniques already know how to deal with them. So very often you don't even have to think about it much, but it's still something you need to be aware. You might wonder, well, I just added this variable. Why isn't this helping me? Well, it turns out that it's redundant with another one. So because in the end you want to understand what went on, very rarely are you happy to deal with black boxes. You want to understand these kinds of things. And then sometimes you want new features or derive some features from the existing features. I use the word feature, that's the common way in machine learning you refer to your independent variables that will help you make your predictions. So for instance, in our problem, you might think of, well, we have a notion of sources of fire, and we have a notion of roadways. But roadways themselves might be sources of fire because people might be camping by the side. There might be accidents, who knows? And it doesn't make sense to have two separate variables. So perhaps there are causal reasons why certain changes in ecology happen due to fire points, due to roadways. But then you want a combination as well. So you might want to find a way to add these two things together or something like that. Or for instance, our data set gives you the vertical distance away from water sources, maybe down to the water table, and horizontal distance away from a river. But maybe what you want to know is the hypotenuse between them. You might be more informed about this if you were an ecologist, but this might be something worth playing around with. So here we just take the Pythagorean theorem and we create a new variable called distance, as opposed to dealing with these horizontal and vertical. And this has been shown to work for this problem, incidentally. This is not something, we're not just groping in the dark. Okay, so what does the code actually look like once you want to create analysis scripts, not just explore it initially? This is the boilerplate code to import what you need. I definitely think that these are the basics for any kind of analysis in Python. Now, onto the guts of the code. Very easy to read in, delimited data in pandas. If you have other separators, so there are like 1,000 parameters to this. You can read in virtually any kind of text data, and there are the packages with which you can read in more sophisticated data sources. Now, the key thing in machine learning is to have a data that you train on and data you test on. What I showed you on one of the first slides is that you may be given supervised data, but you might overfit on it. You might be smart enough not to create a super complex data that will go through all the anomalies. You might know to limit that, but how do you know you've actually been successful? You don't want to test your prediction, test the quality of your model on the same data you trained on, because essentially the computer already knows the answer for that data. So the honest way of doing it is to, even though we hate to lose data, the honest thing to do is to take the data you're given, divide it, only use a portion of it for training, and the rest use for testing. You might play around later with how much data you need for which. 50-50 is definitely a conservative choice. Sometimes you can get away with just 20% of the data being used for testing. But the point is you want to have testing data set. Basically, it's like a blind test. You're pretending like, yes, I know the answers for this data set, for this subset, this test set. I'm separating all from my real data set. But what I'm saying, I'm going to pretend like I don't know it, and I will grade my algorithm based on that, and I'll compare it to the real answers, and then I'll know the real accuracy. So this is what we're doing. Very simple with Numpy. You're generating random numbers for every sample, and if it's above half, then it goes in one category. If it's below half, goes into another. So what you're creating here is randomized true, false indices that will help us to, whenever it's true, it goes into the test set. Whenever it's false, it goes into the train set. There are more sophisticated functions for doing cross-validation, what's called, for doing splitting of data, but this is a very simple way to get started. So now you have completely independent data sets derived from the original one, where you had the answers. You really knew the foliage for every tract of land.
Just a dumb question here. Is that greater than overloaded? I don't understand that line on indices.
The random function generates a 0 to
it generates this many random. So this is the length of our data set. This is how many samples we have. Generate for me this many random numbers.
Right.
And basically, this is sort of like a vectorized operation. It says now for each of them, each of them, if it's above half, say true, otherwise say false. So we end up with, instead of a list of random numbers, we end up with a list of random true and false.
Yeah, I just thought the greater than sign was overloaded operator. That's all. But,
Oh yeah, technically speaking, that's right. It's an overload operator because this is not a scalar operation here. So, and this is something that Python doesn't give you by default. This is what NumPy offers us. So now this is the real guts. So first of all, you would definitely be cheating if you gave it the correct answer at training time. If you give the computer the correct answer and ask it to give you the correct answer, guess what? It will quickly realize this is the most important variable, throw out everything else, and say, here is my model. If you tell me foliage, if it's an oak, I'll tell you it's an oak. If you tell me it's a birch, I'll tell you it's a birch. I am 100% accurate. So obviously, filter out these things. You need to blind the computer. The other things you might want to do, an ID that some bureaucrat gave it, or some was randomly generated. You don't need to, this has nothing to do with ecology, so obviously you know this has to go. Most sophisticated algorithms will realize that this is useless and de-emphasize it or zero out that variable from the start, but some aren't so smart, and you definitely will slow down your learning process, so anything that's obviously useless, throw it out. So now we have basically a list of strings, a list of the names of the columns that we're dealing with, and that's another thing nice with pandas. You can just give it a list of the names of the columns you're dealing with, and those are the columns that it will throw at you. It would be much more difficult to do this if you did it by hand in Python. So you have the feature columns. Now you're actually creating a model, and look how simple it is with scikit-learn. It already has a classifier called random forest classifier. If I have time, I'll explain what goes on the inside. But the point is, this is well studied, well developed in the scientific literature and academic literature kind of classifier. It is very robust against a lot of the problems, physical problems that you deal with. It is pretty good about avoiding overfitting. You don't have to set the number of parameters. You don't have to worry, am I doing a squiggly sort of separator, or is it more simplified? It will build something of the appropriate complexity for your data. There is some hand-holding. You should never consider it a black box, but it's very robust for this problem. You can take my word for it. But in general, you won't know this when you approach a problem. You'll try a few. You have to think hard about what is really inside of these algorithms and which one is appropriate for my problem.
Just to be clear, it's very confusing because we're talking about classifying trees.
Yes.
And that's called random forest classifier.
That's right. That's right.
But there's no relation.
No relation. No. The idea came from for calling things forests is that first there was this idea of a decision tree. Instead of having a tree of decisions, not tree of branches. So the idea was that some data, everything is very dependent. That if you are, for example, at that elevation, and yet the soil type is not what you would expect at that elevation, but for some reason different because of certain irrigation that was done there, then you might find that the tree is this and not that. Clearly, in this problem, we would have these kinds of dependencies. So what decision trees, again, algorithmic notion of decision tree would do is they would find how to construct these conditions to most efficiently separate it into these are the decisions I need to make, these are the questions I need to ask of my data before, and find a way to separate, okay, all the oak went here, all the birches went here, and find the most efficient way to separate it. And it keeps just going through the various kinds of questions it can ask and various thresholds it can put. What should be the, let's say, the soil pH or something like that? What is the optimal way to separate between buckets so we have optimal separation of our oak and birch? So these were decision trees, but a tree can ask so many detailed questions, it will basically become the most squiggliest kind of separator on your data set because it can overlearn. So the idea of random forests was to have many decision trees that are by design dumbed down a little bit. They're given a subsample of the data. So the example here would be, what if I only give these data points? Or what if I only give these data points? And always give a subset. So therefore, even if you have an overly complicated model, if I didn't know about this red data point, even this overly complex curve won't be tempted to dip this way. It would just go straight through. So it pays to blind yourself temporarily, construct a model, unblind yourself, blind yourself in a different way, construct a new model, and take a vote of them. And that turns out to be much more accurate and robust than having a single model. And that's what random forest does. As you see, it's been packaged into Ensemble. There's a whole set of classifiers that's in the literature, and the Scikit package is implemented, called Ensemble, where instead of having one model, you have a whole ensemble of models, and you can choose how many you want, and they're the ones voting in the end for the correct answer. And actually, when I put in estimators, I say that I want 100 trees inside of this forest. I want 100 different models created based on 100 different subsamples of the data. And only once you've examined all of these do I want an answer.
Which in AI, I think, was it Deep Blue on Jeopardy?
I'm sure it uses
the AI, because it uses a bunch of different things and it combines them.
You pretty much have to.
Yeah.
Which also is nice with how to scale computation. You often want to subdivide into different cores, different computers. And it just happens to be a very efficient way to go. Now, this is related to what you might have heard as being called a boosting or bagging approach. So it's a common way to do it. You resample your set with replacement, and it turns out to be very useful. Now, so you construct you instantiate your classifier with these parameters, and this is the key point when you actually do the fit. You take your training data, you say only use the feature columns, don't give out any correct answers, but these are the correct answers that you should know. Find a pattern between these two. And then you might want to ask what the accuracy was. There are very nice functions already implemented in scikit-learn that give you all sorts of things. And there are more things than accuracy. You might be setting thresholds on the certainty that the classifier has, and examine what's the recall rate and what's the precision rate of your classifier. There are combined metrics. There's a plethora of metrics that you use depending on what you care about in your problem. And based on this answer that you get, which in this case was something like 86% accurate, straight out of the box. So based on this, you might iterate, like, okay, I only got 86%. What other features can I implement? What tweaks do I need in my random forest classifier? Are 100 classifiers enough? What you might want to do is to go from 1, which is one decision tree, to 1,000, and see at what point does it not get any more accurate. At what point does it saturate? So you want to basically play around with this, but always understand where you're going, because as soon as you blind yourself, the computer will trick you, and you'll be overfitting, and you're not actually solving the problem you think you're solving.
Very good question. How's the performance of the random forest classifier? Can you say in general?
Hard to say. Depends on the implementation. Obviously, in Python, it will be slower than other things. I can't give you numbers right now, but it's fairly good because you're not doing anything so complicated. You're just going through conditionals, and there are certain ways that you can help yourself. It caches certain results from certain samples based on certain nodes, and doesn't have to try them again and so forth. I can tell you.
Are you using it in your production environment?
Yes, this is my workhorse for sure. And once just to see how it works, and I've known the challenges, and I know the difference in efficiency. So they're doing good things under the hood. Okay, so iterate. You got an answer. What can I do better? You might ask, well, which features ended up being important? By IISO elevation was important, but there are like a dozen other features. I didn't show you there are 30 different soil types, and the data has information about which types of soil are present in that tract of land. So very easy in Python, and with the tools you have, once you did the fit, the classifier knows what are the feature importances based on the order of the features that you fed them in. So zip them up to be pairs, the name of the feature and the corresponding feature importance as computed by this random forest classifier. And let's sort them in reverse order. I give you only the first 3. There are dozens more. And you already see elevation seems to have been the most informative one. And as you saw, it offered pretty good separation between foliage types on the plot I showed you earlier. Apparently, distance to roadways was important. We are impacting our environment. It's pretty clear. So as you see very quickly, the importance drops. And as you're designing your new features, you will be refitting, looking at importances, and see whether the new ideas you came up with got to the top of the list, whether you're contributing. If every idea you're putting in ends up at the bottom of the list, chances are you're not actually putting in new information, new intelligence into your modeling.
From a development standpoint, especially if you're doing work for clients, I can see that getting the list of the feature importances, if you have to explain your work, which we often have to, which is horribly complex. It's too complex to really fully explain, But something like this, we can take like the top,
Absolutely.
5 features, put that in a presentation, and talk about the most important ones to the client.
Yeah, very few people want to have a black box. They want explanations. So you don't want a black box, they don't want a black box. I was actually recently talking to some people doing machine learning at marketing firms, and they say that, well, the clients always want to know, well, which campaign was important? Don't tell us, here's a new formula about how to optimize your new campaign budget. What was important? What should we de-emphasize? Why was it important? What was the interaction between different marketing campaigns? So this may be even more important than the final result. So you might be tweaking. There are various criteria based on which splits are done in these decision trees, based on entropy, which means how much information gain have you got, how good a separation you got per node of these trees. Or you can go based on impurity. Those sorts of things you can do, and these tweaks will be different for different kind of classifier models you're using. You want to understand the trade-off. You want to give yourself as much training data, but leave yourself enough testing data to understand how you would perform in the real world where you don't have the answers. And then you might have to really understand your algorithms and know what shortcuts you can make. It happens that with random forest, you don't even need to separate into train and test data. It does it internally. Because for every classifier in the ensemble that it makes, it blinds itself to a subsample of the data. Those called out-of-bag samples can actually be used to do a test. So it remembers which classifier was blind to which and computes accuracy based on that. So you can actually give it all the data and still know what your true accuracy may be. If you're not dealing with a sophisticated classifier as this, what you might have to do is work on this project until you're happy with how close the training and test accuracies are. And then once you know that you're not overfitting, you've done everything well, give it all the data. Because at that point, you don't care to keep the separate testing data. You don't care to blind yourself. You want to give yourself as much data as possible and then move on to real world classification.
I have a question.
Yeah.
You find very often that you have to retrain models once you get into like a production environment again?
Well, very often
Depends on the quality of the sample.
Conditions change. That's right. Very often, what you fit is only relevant for that month, and you have to do this again.
Okay.
And what are big problems these days is what has to be solved with what's called online learning that I'll get to now. That you have gigabytes of data just streaming through, and the situation keeps changing. You have to keep retraining yourself on what to offer the next day, whether to clients or weather forecasts and so forth. So you might not want to forget the training you did. You want to do iterative learning. So maybe there are broad patterns that you know from the past, but you want to do corrections. And how much you learn, how much you forget is another important parameter that you'll be tweaking. I have to kind of move on a little bit, but yeah, so we're getting to scalability. Simple multi-threading is possible. Most of these were ensemble methods, so all these sub classifiers can be working in parallel on different threads, and scikit-learn is already well matched for this. If you just give it a number of jobs, number of threads you want running simultaneously, or give it -1, it will just run according to the number of cores that you have. What if it doesn't fit into your memory? You will have to train in mini batches, what's called. Now, you have to be careful because sometimes to get numerical independent variables from what you have, let's say you're given text data, there are no numbers associated to it. You need to get those numbers from the linguistic analysis, from term frequency vectors and so forth. This is beyond the scope of what we're talking about here, but sometimes you need to know your entire corpus. You can't afford to just deal with a small mini batch. So there are various ways to do things, to vectorize, to create your features, your independent variables on the subsamples, and remember the state of that vectorizer, forget what you have, load something new in memory, and then correct it and augment that. But this is beyond the scope, but you have to bear in mind that there are trade-offs if you can't do it all and fit it all in your memory. And then there's incremental learning, as I mentioned. You remember some of the patterns you've learned before, but as the new data is coming, you're refining your model further. And certain kinds of models are good for this. Random forests are not in this case. And these are the models that could adapt as you're learning on the fly. And now, if you're not fitting in data and you have huge amounts, and you need to distribute data across many machines, that's where you're in the terrain that's been called with a lot of hype, big data. And one of the best tools I find these days is Apache Spark. It works in the Hadoop universe, if you're familiar with this, but it can be independent of that as well. It can run on Mesos, it can run standalone, it can access various types of distributed file systems. So I find it very well developed and robust, except that the machine learning aspect of it, which is just one thing that Spark does, is not as well developed as scikit-learn at the moment. Most run-of-the-mill problems are already well developed in that. It won't be quite as easy as the simple Python code I've shown you. I'll show you an example of the code in a moment. But chances are, if you're dealing with a problem where you're swamped with data, sounds like you have enough to make your models and decisions. Your problem won't be the algorithm sophistication, but how to handle the amount of data. So it might be a reasonable trade-off to go to this tool where it can handle the data, but doesn't have a sophisticated set of tools. But I think within a few years, it will catch up to scikit-learn. So how does it look like? Unfortunately, you have to run in a specialized environment where Spark is running. You have to load in the context of Spark because it needs to communicate with the machines to which you'll be mapping your operations and then reducing the result back to the machine, the master machine. I don't know if people are familiar here with the MapReduce model of parallel computation. You see, so it's a few extra lines of code to get yourself started. This is a very simple regression problem. I think this is from one of their examples. In this case, we're just loading a simple text file, but in reality, you'll be loading what they call RDDs, these distributed data samples. In parallel, you're loading them up from your machine, not physically transporting that to your master because that would defeat the purpose. You're saying that be aware you'll be loading it from your distributed data set. This is how you'll go about it once you map your processes onto the machines having the data. You load in your model, you train it, and then to evaluate it, because the data might be out there, again, your test data might be out there just like the training data on remote machines, you have to map the evaluation of the accuracy, do the prediction on those machines, and then reduce it back, and then calculate your, in this case, the mean square error. Yeah, so just focusing on different parts of this code. So let me conclude. I think we're running out of time. I hope you see that it's now what was called rapid development in general. Python is also rapid development for machine learning. We have pretty large scale. We have tools for large scale data that are catching up in their sophistication on the level of algorithms with what was available for in-memory calculations and give you the scalability. And you see that where in the past you had to think very separately, that there are computer languages, there are compilers, and then there are the nice interactive environments like MATLAB and Maple and so forth. Now the distinction is blurred. At one point, R, programming language with its shell, had the dominance of doing statistical work. Now you can do much of that in Python. They're very nice Python shell environments, very nice plotting tools, very nice high-level data structure packages. So, so you're all set to do your exploratory analysis and your real production-worthy code right there in Python for machine learning. And this is what we do. This is not something I have to do homework on. This is what we do every day, and it's a lot of fun at Espertine. So let me know if you have any questions.
Yeah, question.
How do you find the quality of the Scipy package?
Quality. I've only had to use a couple of functions, and so far they haven't disappointed me. I would cross-check, as a rule, I would cross-check against other calculators, other packages to see whether it doesn't have some region where it miscalculates something. But what has been your experience? Sounds like
About 50% disappointed.
50%. What sort of functions were you using? What type?
Like just like statistical functions usually. Like they're all just like random seeming bugs or odd limitations or like very strange interfaces.
Oh,
so half the time it's great, it solves my problem, and then half the time I get some terrible result, and I wonder what's going on.
Is it correct, or is it that you
could be just I'm behind the curve? My library is a few steps behind. I tend to work on a system that was run by some other sysop, and it's not really up to date.
Well, maybe I was lucky
keep
to avoid the
finding it.
minefield, but I think that's the best we have right now for Python, which I think will evolve. Wasn't that a question?
Yeah, have you done similar things much in R? And if so, I'm curious to hear the pros and cons of.
Yeah, unfortunately, yeah, good question. It would be nice to give you a comparison because that's often the question asked at the beginning of an analysis project. Should I do it in R, which is so mature in terms of statistical packages, and there's so many high-level operations you can do on it, and how does it compare with Python?
Especially as a beginner.
Right. I think they're so well matched right now that that it's the more important question is what are you comfortable with? But of course, you have to ask, where is this project going later? If you're going to have to translate everything into another programming language for production, be it an academic package that'll be running over a huge amount of data. I worked in particle physics where we had to do this exploratory analysis from the start in C++ because we knew things have to run at a very high rate on the actual machines coupled to our detectors. So it's an important question to ask, like how much labor are you willing to undergo to then change over just because you're more comfortable in your initial stages. And that's something you have to ask about both R and Python, because if you really need the performance, then there are a few tricks to get you somewhat close, depending on your problem, to C, but sometimes it's pretty lost cause. And one of the things you have to think about, in addition to what is the right algorithm, is where should I put my efforts in terms of optimization. Very often you might do something like have the overall framework done in easy language like Python, and then introduce a nice compiled package there or wrap something. Thankfully, most of these math packages like Numpy, Scipy, scikit-learn, they do have a compiled core. It's not all Python.
Sorry to interrupt there, but it's 10:55, so we've got 5 minutes before the next session.
Okay. I welcome private questions as well.